That introduction. And thanks to all the organizers for the opportunity to come and present this work and to visit IIT. I've come very often, as many of you know. So I think I was actually in IIT already last week, in the end of December. So this is already my second visit to IIT this winter. This work that I'm going to present is a joint work with Chuk-Ting Lee. He was a postdoctoral fellow of mine at UC Berkeley for the past couple of years. And he's now just taken up a position as an assistant professor at the Chinese University of Hong Kong. And this is what he looks like. So, so if you see him around, that's the guy who did most of the work. So what this talk is about one-shot information, what's called one-shot information theory, or finite block length information theory. This is a field that sort of got started maybe a little over a decade ago, and the motivations were to try to deal with what's considered one of the big weaknesses of Shannon's program in information theory, which is that it's asymptotic in nature. It deals with large block lengths. And the general paradigm in this one-shot information theory is to go away from trying to prove just, very beautiful-looking limit results, and to instead give explicit bounds on what is possible with just a few uses of a communication channel. So that's kind of an open-ended program, because when you are in the business of giving explicit bounds, you can always get better bounds and so on. So there's a lot of literature on this kind of activity. Bounds are generally of the first order nature, which are trying to get close to something like capacity, as Shannon does. And then the next step is a second order nature, which is sort of like studying fluctuations, Gaussian fluctuations. Some people are even proving third order results and things of that sort. One of the, so to speak, goals of some of these bounds, apart from their getting upper and lower bounds which are close to each other, is also that they should somehow get, when the finite block length gets bigger and bigger, they should also match the asymptotic results. So a very large number of results of this sort. And information theory in the traditional Shannon sense is also a very large field with many specific problem formulations that people study. Some of them are very complicated in the multi-user case and or lots of open questions, etc. So there's a big room for playing in this entire landscape. What we've done in this work is provide a new technique for proving these kinds of results. And the technique has got some virtues to it. One of the virtues is that it basically seems to be able to recover the best known results in practically all the problems that people have studied. Now, when you make a statement like that, obviously, as I said earlier, the people have only done certain kinds of bounds, so presumably they can do better bounds with their techniques eventually by going to higher order, etc. And also, in some cases, it's not exactly the best. In some cases, it's better than the best, etc. And largely speaking, it's able to recover the first order and the second order results. And the way you would illustrate that is by just showing that you can do it in most of the kinds of specific information theoretic problems that people study. So that's the structure of the talk. I mean, I'm going to just tell you what this technique is. The technique is based on using Poisson processes to randomize. You've got to do some kind of randomization in information theory, particularly in the finite block length. You've got to hedge against uncertainty. So existing proofs also use various kinds of randomization. So from one point of view, all we've done is provide you with a different way of doing randomization in the finite block length case. But because of the beautiful properties of the Poisson process, which has sort of built-in independence at all over the place, the proofs end up being magical. In fact, the proofs that we have are so short that even though we are dealing with the finite user case, the proofs are sometimes shorter than the asymptotic proofs that are known in the literature. And in effect, we're able to recover all these things. Now, my own interest in this actually is slightly broader, in that you should really think about this as a way of trying to do non-asymptotic randomization in a way that extracts the likelihood ratio. I think that's the highest order bit to get out of this technique. And since the likelihood ratio is what sort of drives all of statistics, I don't think you should think of this talk as necessarily being just an information theoretic talk. I mean, I'm giving a talk that's purely information theoretic, but it's potentially might have applications in various kinds of scenarios like randomized algorithms, various statistical machine learning problems, etc. So it's sort of like non-asymptotic randomization. Of course, we all know how to do non-asymptotic randomization. You just toss a coin or you roll a die. It's non-asymptotic randomization, right? But it's kind of built on the, because it's built on the Poisson process, it works like magic. So we've encapsulated this in a lemma that we call the Poisson matching lemma. And the goal here is to, is basically, we set up a certain kind of Poisson process. The Poisson process is going to have a space dimension and a time dimension. And we're trying to basically capture probability distributions on the space dimension by picking points in the time dimension. That's the essence of the technique. And since we want to capture the likelihood ratio between two probability distributions, we basically consider 2 points. And what I'll do in this talk is just illustrate a whole bunch of examples from various kinds of specific Shannon theory problems that have been studied for decades and ad nauseum at some level. So this will be basically channel coding problems, source coding problems, joint source channel coding, some multi-user problems, where honestly the techniques that we have are not really that satisfactory. We were trying to get away completely from codebooks, and we haven't been able to do that completely, so I'll discuss those. And also some things that are more connected with simulation, what's called channel resolvability in Shannon theory. So if you don't know Shannon theory, some of this might even be new to you, so I'll try to be slightly careful in defining the problems. But anybody who's actually working in information theory knows that this is the bread and butter of the community. So as I said, this is just sort of like looking towards other directions. So, so in the multi-user things, we actually have to use something slightly more general, which we call the generalized Poisson matching lemma. So we have to provide a mechanism that sort of looks like randomization. So rather than picking one point which has a distribution, desired distribution, we have to provide a mechanism that looks like it's providing some kind of randomized codebook. So rather than picking one point with a distribution, we pick a bunch of points. And we get some kind of IID sequence of points with that distribution. We need that for our multi-user results. So that's called the generalized Poisson matching lemma. And another paper that's not at all related to this, also based on this Poisson matching technique, is addressing questions of what's called optimal transport, how to move one probability distribution to another. And we've used this to study the question of having, let's say you have 10 probability distributions, and you want to try to be able to simultaneously couple them so that the pairwise optimal transports are within a bounded factor of what you could do if you were just dealing with that particular optimal transport. We're able to characterize those constants, etc., using this technique. So that's a non-information theory, in some sense, use of this technique. So I'm not going to talk about that, but just to tell you that this general idea might have many further manifestations. So this is the first problem that many of you would encounter when you study an information theory course, is a problem of channel coding. And this is the traditional Shannon formulation. So n is the block length, and n is eventually going to go to infinity. There's a conditional probability distribution here, P of y given x. X and y are random variables drawn from finite sets. So the idea is that the encoder, which is the guy stuffed to the left, is going to, at each time, put in draw an element from the alphabet of x, and that's going to result in the receiver receiving y, which has got this conditional distribution. So the encoder desires to send a message from a set of possible messages, and it maps each message to a sequence of inputs, and the channel acts independently from time to time, so you get a sequence of outputs. The decoder is supposed to recover the message. As you can imagine, if the channel is noiseless and you have n uses, then you can expect to be able to send exponentially many messages, so that's the correct scaling. R is called the rate, and basically if you can get the probability of error going to 0, you say that you can communicate at that rate. So I already said all this, right? So encoder observes the message and outputs the sequence. The decoder observes the output and estimates what the input is. So Shannon's channel coding theorem basically says that what you need to do is to imagine the mutual information across this channel and maximize it over all input distributions. The threshold for what rates you can actually communicate at, and you can't do above that, and you can do below that. And information theory being an engineering subject, there's very little that people don't bother about what happens at the boundary. Mathematicians would always spend their time worrying about the boundary. This can be proved using techniques that are called typicality in the information theory literature, but basically boil down to the law of large numbers. So you kind of study, if you have long sequences, they tend to exhibit the statistics of the input. So you somehow convert the problem into something that looks like a deterministic problem of packing in spheres inside a big sphere or something of that sort. If you know information theory, you know what I mean, but that's a rough idea of what the traditional picture looks like. The one-shot version that has been popular over the last decade or so, is the version of this problem where you don't have asymptotics. So you have this channel once again, and all you get to do, basically the encoder has a message, and all it gets to do is use the channel once. So it has a message drawn from some set of size L. It chooses an input X randomly. The output Y is conditionally distributed according to the channel, and the decoder has to try to recover M hat. Clearly, I mean, there's little chance of getting the probability of error to go to 0 or anything like that. For one thing, no asymptotics at all, right? So it's kind of a trade-off between how big L is and how small the probability of error can be. And ideally, you'd like to get some bounds that are asymptotically good. So that's a setup. And one of the best-known results is that of Polyansky. I think this is Polyansky, Poor, and Verdu paper, which gives you this, this estimate for the probability of error. So the way you want to think about this is, you're using the input distribution X. There's this quantity called the information density. The information density is a function of the input pair X, Y. So X and Y are drawn from finite sets. So it's basically measuring the likelihood between the joint distribution that is caused by the channel when you input X and the product distribution where the X and Y are separately independent with their own marginal distributions. But you do it at the log scale, and the expectation of this object when X and Y are distributed according to cap X and cap Y is basically the mutual information across the channel. So it's sort of like the quantity that goes into the guts of Shannon's mutual information. Actually, you want to think about information theory as being entirely dealing with expectations, which is largely that's what it's been doing. And people have increasingly been studying the distribution of the information density, the so-called information spectrum techniques and so on, right? So there's much more juice in the information density than in just the mutual information. So at the level of this one-shot stuff, what you end up basically proving is that you can arrange this communication scheme that's in this paper of Polyansky et al. To get the probability of error to be upper bounded by this quantity, which depends on, so this gives you some idea of the trade-off between P sub E and L when you happen to use a particular distribution X. Now this is an interesting result because if you treat the large block length problem as if it were a one-shot problem, this bound is good enough to recover Shannon's result. So if you replace L by 2 to the nr, and you now start to replace X by Xn and Y by Yn, then you can sort of make this thing roughly n times the mutual information. It's more or less a law of large numbers fact, and then you end up recovering Shannon's result. This is a result that we can basically recover using our technique with a shorter proof. I'm going to give you many such examples. Now, the way this was proved actually in the Polyansky paper, Polyansky et al. Paper, is also uses randomization. So what they do is they basically generate a random codebook. So for each of these messages, just a finite number of possible messages, L of them. So think of L as 10 if you like. So I'm the transmitter, I've got to send one of those 10 messages. So for each of those messages, I generate an input, randomly I generate an element of the input alphabet according to the distribution P sub X IID. And I encode the message M. So if I want to send the fifth message, then instead I send the corresponding input to the input alphabet symbol X of M. The decoder receives Y, and what it does what you would expect, it does maximum likelihood decoding. So the codebook is supposed to be known to the receiver also. And given Y, it chooses as its estimate of the message the one that minimizes, that maximizes this conditional probability of X of M hat given Y. Of course, there might be ties, and then you have to break ties somehow. Here's a picture for what the traditional viewpoint is, right? So let's say that the input alphabet has got size 5, and L is 4. So there are 4 possible messages. In effect, what you're doing when you choose a random codebook is for every message you're choosing at random one of the 5 inputs to put in. So here, for message 1, this realization of this code book is you're going to send the symbol 5. For message 2, you're going to send the symbol 4, and so on. And the receiver sees y, little y, which is generated by the channel based on what input x was put in. And then it just does maximum likelihood decoding. It has access to this picture and just decides what the m is. That's basically one way to think about what's happening in the one-shot problem. We're not doing anything very different at this high-level, conceptual level, but what we're going to do is we are going to basically use a Poisson process instead of this fixed-size code book. And I'm going to explain this picture a little bit more carefully, but roughly speaking, what we're going to do is we're going to pick the input to send basically by setting up a Poisson process on the product of an appropriate space dimension and time. So we're going to create this random code book using Poisson processes. And then it turns out that you can set up a way for the decoder to decode, which leverages the magic of the Poisson process to give you very, very simple proofs, which are also good enough in the asymptotic sense. And in many cases, recover essentially the best known result, even in the finite block length case, and beat it. That's sort of the big picture. This picture will become clearer as I go along, but might not be the best place to describe it. So here's a little, so to speak, schematic of what we have accomplished. The asymptotic situation is when the block length is going to infinity, generally based on typicality ideas. Proofs are, so to speak, simple, but actually at this point, people can't use this typicality technique in a very efficient way for general alphabets. They're only using it for discrete alphabets, which is all I've discussed so far. The one-shot techniques are strong enough to deal with both discrete and continuous alphabets, but from our point of view at least, the proofs are kind of complex because our proofs are simpler than the existing proofs. Block length is finite. So what we sort of accomplished is give you a technique that gives you the best of all worlds. The proofs are very simple, certainly simpler than the existing proofs. Works with all general alphabets, so we can work with Polish space alphabets, no issues. The technique just works. And block length is finite, that is one shot or simple shot, etc. Plus, I think for me, I think of information theory as just one subject in an ocean of subjects, and statistics as such is much broader than information theory. So I think there's also randomized algorithms in computer science and many, many places where you might want to use, so to speak, finite techniques for randomization. And this is another tool for doing that. So that's really the broader picture. Okay, so here's the guts, and the guts actually come from earlier work of Chuk Ting. When he was a student of Abbas, he graduated, I think, 2 years ago, and then he came to do a postdoc with me. So this idea of trying to use a Poisson process to represent a distribution is captured in this picture. So the space variable here is something called U, and our goal is to create a probability distribution on the space U, but we do that by picking a point from a Poisson process. So what we do is we set up the Poisson process in a space-time region. So time is going vertically, the space is going horizontally. We have some probability distribution on space which is serving like a base probability distribution. You can think of it as a uniform. It doesn't have to be a probability distribution. It's a measure on the space axis. You can think of it as the uniform distribution in this case if you like, whatever it is. And then we think about the Lebesgue measure going in the vertical direction in time. And we set up a Poisson structure which has intensity basically defined by the product of the space measure and the time measure. So if you think about this x-axis as unit interval, then, and you think about it as supporting the uniform distribution, then on the product of the unit interval and non-negative real axis, I just create a Poisson process with uniform intensity measures. I just have this bunch of points. I want to create I want to pick a point from this Poisson process with the property that the space coordinate of the point meets a certain target distribution, P sub U. So what I do is I look at the likelihood ratio of P with respect to the base measure mu on the space dimension. So say if mu is uniform, I'm basically looking at the likelihood ratio of P with respect to the uniform distribution. And that is, you want to think of that as some kind of graph whose abscissa is the space coordinate, and you want to think about its ordinate as defining some kind of shape The likelihood ratio is defining some kind of shape in the vertical direction. And then you just grow that shape linearly in the time axis. That's basically what's going on. So for instance, if this is a shape, the shape would initially be small, then it get bigger and bigger. And because it's some funny nonlinear kind of shape, there's some point that it touches first. And you pick that point. And you can prove that the space coordinate of that point will end up having the distribution that you wish. This comes from Chuk-Ting's earlier work with Abbas. So in terms of math, what you're doing is you're looking at the time coordinate divided by the likelihood ratio at the space coordinate, and you're choosing the point for which this ratio is the smallest. So an equivalent description is that you look at the likelihood ratio and you grow it in the time direction, and you fix the first, basically pick the first point that you get. That's equivalent to this. I hope that's clear. So the points, you might basically, the Poisson process has got a countable number of points, so you can index them in some arbitrary way. So those are these indices. So this is, I call this point 1, point 2, point 3, whatever way I like it, like to index it. And then I pick the point with that index, k, for which this ratio is the smallest. It's like another way to think about it is that I want to choose dp by d mu ui. So I want to multiply this dp by d mu I by the smallest factor so that I end up getting a point of the process. And that's the point that I... And you can prove that the space coordinate is p. So to really understand what's going on, it's easiest to think about some simple case. So suppose that my space coordinate has just got k points in it, so it's discrete, and I let mu be the uniform distribution on these points. So I want to think of this as a measure, right? Maybe giving mass 1 to each of these points. So I want to create a probability distribution with p sub k on it. Now, in this case, the Poisson process is going vertically, and I just got k points in here, so maybe k is 7 or something. So I've got these 7 lines. Each of them is supporting some Poisson process, and everything's uniform to start with. So all that's going to matter from this mental picture is the first point along each of these lines, right? So I basically got 7 exponential random variables with rate 1. And those are called tau 1 to tau k. So those are my tau k. And what I'm doing is I'm moving in a way that is defined by the likelihood ratio. So I'm picking that j for which this ratio is the smallest. And if you know anything about exponential random variables, you realize that I end up picking j with probability pj. That's basically what's going on. It's a minimum bunch of exponentials of different rates. So that's what's in the Poisson functional representation. Now, what we ended up doing is going beyond this to extract likelihood ratios. But just to understand the Poisson functional representation better in some pictures, so here let's say that your likelihood ratio is constant. Then you're basically going to pick the point that you're going to pick a point, so to speak, uniformly at random. The space coordinate of the point is going to be uniformly at random. Here's another picture. So let's say that your likelihood ratio picture is like this. So even though you've got the probability distribution you're trying to create is supposed to now be uniform from half to 1, then you're growing this shape, and you're always going to pick a point that is only on the right half side, and is going to be uniformly distributed on the right half side. Right? So those are kind of pictures. And the most general picture is something like the earlier one that I had. So if you pick some shape and you grow that shape, you'll end up picking somebody whose space coordinate is distributed according to this density. Does that make sense? Happy to take questions at this point. So we haven't yet defined what I haven't yet told you what the Poisson matching lemma is. This is just the Poisson functional representation. So this is what Chuk-Ting came with, and we started to ask ourselves what we might do if we were dealing with multiple distributions. And so here is the Poisson matching lemma. So the Poisson matching lemma arises from asking the following question. Suppose instead of one probability distribution, I've got 2 probability distributions, P and Q. So I create the Poisson functional representation for P and the Poisson functional representation for Q. And it's natural to ask, when are they the same, right? So if P is closer to Q, they're likely to be closer to each other. And somehow then, when they happen to be different, it's giving you some way of discriminating between P and Q. So it turns out that it basically ends up capturing the likelihood ratio. And that's what makes it so powerful. So you can prove the following fact, which is that the condition on what the space coordinate corresponding to the P distribution is. That is, U tilde P is the spatial location of the point in the Poisson process that is the Poisson functional representation of the distribution P. So condition on that, the conditional probability that, or on its value, the conditional probability that the space coordinate of the Poisson functional representation for Q is different can be upper bounded by this expression or by this expression. The basic point is that these things are related to the likelihood ratio of P with respect to Q at the point which is the Poisson functional representation of P. It's also rather easy to understand if you decide to back away from abstract looking junk and deal with the simplest case, which is a discrete case. As with anything, I've got a typo here, I'm sorry, this is about U tilde sub Q. So, as with anything involving Poisson processes, it can't possibly be difficult, right? Because everything in Poisson world is easy at some high level. So, there's actually an exact formula for this quantity, and the exact formula turns out to be this. And the way you understand this is, okay, let's consider the case we just got k points in space, and the base measure is uniform, or it's more precisely, it's a measure which is equal to 1 at all these points, and P and Q are these probability distributions. Then you want to compute this conditional probability, you might as well just consider the case where U tilde P is 1. You can just write down an explicit formula for this. And the explicit formula for this, it's easy to see, is this. Basically, the numerator is that both the first and the second distribution end up having the first point as the winner, and the denominator is when the first distribution has the first point as the winner. That ratio can be manipulated to look like this in the general case. And this can be shown to be basically bounded by the expressions that I wrote down earlier on the previous slide, which are these expressions. So that's all there is to the Poisson matching lemma. Okay? It's no big deal. But the thing is, it turns out to be so powerful. So that's the point I'm making, is that it's just magical in terms of what it's able to do. And I just want to make, in this talk, I just want to make that point in a bunch of information theory problems. So it's a versatile lemma. It turns out that information theory is thinking about both asymptotic and non-asymptotic problems. Nowadays seem to think in terms of certain lemmas that are used as machines in many of these problems. Packing lemma, something called the packing lemma, which is related to channel coding. The covering lemma, which is related to rate distortion and source coding problems. Soft covering lemmas, which are also related to resolvability and also to lossy source coding. And all these lemmas sort of just go out of the window when you think in these terms, in that you can just sort of write down straightforward proofs directly at the level of the likelihood ratio or the information density. And we are basically able to even strengthen the best results in many problems. And the proofs are much, much shorter. So I'm going to illustrate that in the rest of the talk. So let's deal with the one-shot channel coding problem. So it's the same problem that I had earlier. So I've got this channel, conditional probability of y given x. The transmitter wants to send one of L messages. And to each message, it gets to choose a random input into the channel. Receiver sees a random output and decides what the message was. So what we're going to do is we're going to use the Poisson process to encode. And the space coordinate for us is going to be the product of the input alphabet and the message space. So the message space is 1 through L. If the input alphabet is discrete, let's say it's got size 5. So this is basically 5 times a space of size 5 times L, on which we create the distribution Px cross Pm. We get to choose Px later to optimize. And this is basically this is just the base measure. So on the base measure, we just take this as our base intensity measure. And lambda stands for the Lebesgue measure. So in the time direction, we have the Lebesgue measure. So we just create a Poisson process with this intensity. So there's just a bunch of points sitting around. And we're going to use this Poisson process in order to decide how to create the random codebook, using the idea that was described earlier. Now, from the point of view of the transmitter knows what message it wants to send. So it knows exact value of m. So the probability distribution that it's going to try to use in order to create the point to send is going to be based on this distribution, p sub x, which it gets to choose also, but we think of that now as being fixed. P sub x cross delta sub m. So it's focusing only on the portion of the spatial coordinate where the message is exactly m. And it just uses the likelihood then of this distribution with respect to that distribution and goes through this business of growing the likelihood ratio and picks out the first point that it hits. That point is going to have a specific x coordinate, and that's going to be the x that it sends. That's the idea. Now the receiver gets Y. The receiver is uncertain about what message was actually sent, so it sort of encapsulates its agnostic nature about that by just continuing to use the uniform distribution on M. But the receiver has access little y, so given that the little y came out across the channel and the receiver is supposed to know what P sub x, the distribution that the transmitter is using, it can use Bayes' rule to basically decide what's the best distribution to apply to x. Should be the conditional distribution given the actual realization of what it saw. It's going to use that as its distribution, as its probability distribution to construct the likelihood ratio from which to pick out a point in the very same Poisson process. The Poisson process is thought of as common randomness between the transmitter and the receiver. That's equivalent to the traditional viewpoint that the realization of the random codebook is known to the transmitter and the receiver. That's it. So this is basically, this pictures encapsulate what's going on. So the decoder is basically going to use this distribution, and now you just use the Poisson matching lemma, right? The probability that you make an error, that is the point that the receiver picks out from the Poisson process, is different from what was actually transmitted, that probability can be written as, can be upper bounded by this conditional probability, as you can see, because here I have the chance that any one of these coordinates is wrong. And this thing is the kind of thing that we just wrote down. I mean, you sort of picked out the point u tilde p. What's the chance that u tilde q is not equal to u tilde p? So the u tilde q, the q there is from the viewpoint of the receiver, and the p is from the point of view of the transmitter. And the likelihood ratio just pops out. The likelihood ratio pops out. It means that the mutual information pops out. Information density pops out. And that's it. I mean, this is essentially the Polyansky result, except we're slightly off here because we got L instead of L minus 1. So in some cases, we're not exactly right there, but this is basically what we get. So this probability, this calculation basically gives you this. And that tells us that there must exist some fixed codebook that actually achieves this probability of error. And this is good enough to get you the asymptotic result. And it turns out that this technique is also good enough to recover what's called the channel dispersion, which is the second order result in this context, dealing with the fluctuation behavior. I better check on time. I mean, I just want to run through some examples like this. That's what the rest of the talk is going to be. So one reason is for checking on time is also to make sure I don't finish too fast. So it looks like I have, how much time do I have? Just a few minutes, I think. Huh? Only 3 or 4 minutes? Okay, good, yeah. So I think I've got the main points across. So what I'll do now is just run through what we do for various cases, but I also need to tell you about the generalized Poisson matching lemma. So I'll be very fast in the rest of it, and then maybe focus a little bit on the generalized Poisson matching lemma. So another thing we can do is deal with channels with state information at the encoder. So this is when the situation which is a generalization of the previous situation, where the channel actually is also, the transition probably depends on some state. The state is known to the encoder but not to the decoder. So state is denoted by S. The channel is now P of Y given X and S. Encoder produces input based on both the message it wants to send and the state. The decoder has to recover it only based on the output. The asymptotic result that's known in this area is called the Gelfand-Pinsker result. And it's basically the supremum over all conditional distributions of an auxiliary variable given the state, and a mapping of that tells you the input given the auxiliary variable and the state of this difference in mutual informations. There's a positive part down there. What do? We set up a base measure, which is some PU cross PM cross lambda, and we encode based on a likelihood ratio, and the likelihood ratio is basically going to use the appropriate P of U given S, and the actual message that you know. So you get to basically choose these as parameters, and I guess you want to think of these also as being some fixed parameters, fixed before the transmitter and the receiver act. And you decode using another distribution which is agnostic about the message, but uses the received output as to decide what the conditional probability of the auxiliary variable is. Write down the Poisson matching lemma, 4 lines, that's it. This is a complete proof. And it gives you something which is asymptotically accurate, and turns out to be actually, it's a one-shot bound that achieves the best second order result. And is in fact stronger than the best previously known one-shot bounds, which I've got very, very long proofs. 4 lines, okay? That's the end of the proof. So that's just give you an idea. So So similarly, we've worked with, so you can study the problem of lossy source coding. The source coding problem, the transmitter is not really trying to send a message, but it's trying to send a symbol from a source. It encodes it into some point from a finite set. The receiver sees that point and then tries to recover what the actual input symbol was. But in the case with distortion, it recovers it from a different alphabet, and some distance metric should not be too big. So you're trying to control the probability of excess distortion. The result that's known here in the asymptotic case is called the Wiener-Ziv result, and it's some formula like this. There's an auxiliary variable u. You get p of u given x. You get to choose that, and you get to choose the mapping that the receiver uses to create its estimate of x, with the guarantee that in expectation the x and z variables are not different by more than capital D. So something like this. Okay, so well, we do the same sort of thing. We create this Poisson process based on some base measure. This is our mu. Lambda, remember, is Lebesgue measure. We choose the input distribution to work with, which gives you the likelihood ratio with respect to the base measure, and that involves the choice of this auxiliary distribution p of u given x. And now the m is basically being chosen by the encoder. So the encoder is the one that's agnostic. The receiver sees the m and sees the y, so it uses both. It sort of conditions on both of those and uses the Bayes rule on the distribution of the auxiliary variable. Apply the Poisson matching lemma. Complete proof in these 5 lines or 4 lines or whatever you want to say, 4 steps anyway. Stronger than previous known one-shot bounds. So that's the situation. Okay, so let me, in the interest of time, let me skip some of these slides, but I'll just tell you what the generalized Poisson matching lemma is. The generalized Poisson matching lemma, we were sort of forced to come up with this because in multi-user problems, it turns out you got to use with multiple code books, so we had to do multiple code books. Ideally, we shouldn't be able to do that, shouldn't have to do that. But what we do is basically we create successive points from the Poisson process, which basically give you an IID sequence of objects in the space dimension, which all have the distribution P. So we pick out our first point, then we pick out our next point, we pick out our next point. And now, what we want to do is we want to think about this for 2 different probability distributions. So here's just done for one probability distribution. So we'll pick out this sequence of IID spatial coordinates by picking out the points one by one by growing the likelihood ratio. Now, if you have another distribution Q, you can do the exact same thing for Q. The point now, what's interesting now is that the order in which the points come under Q is different from the order in which they come under P. So what we can prove is that you have some control over that. That is, if you think about the point that is the kth point under Q, which k serves as the kth point under Q which matches the jth point under P, right? That's what this notation is. Then you can bound the expectation of that by the likelihood ratio at that jth point. But it's j times that because you've got j steps. So you've got some control over how much dispersion there is in the reindexing under Q relative to the reindexing under P. I know I'm running out of time, so let me just quickly tell you how this works in, say, problems like the broadcast channel. So the broadcast channel is when you have a transmitter trying to send messages to 2 different receivers, and there's the best, this is an unsolved problem actually, finding the capacity region even in the asymptotic case. Best known result is Martin's result, which gives you a rate region like this. And the way we get it in the one-shot case is somewhat like a bit of a kludge. So what we have to do is we've got to create actually a sequence of points based on an auxiliary variable for the first coordinate, and then to create the second coordinate based on an average over the locations, so to speak, of that sequence of points of the first coordinate, and then recover the auxiliary variable point that we use for the first coordinate. So this is not very happy, but it's happier than the existing proofs anyway in the one-shot case. And we are able to basically give you one-shot results that asymptotically give you Martin's result. And previous results required 2 subcode books, 1 for each of the guys. We've managed to get it down to 1, but ideally we'd like to have no subcode books at all. So I won't bore you. We can also do distributed lossy source coding. The slides are available, and the paper is already on archive and has been submitted for publication. The technique is exactly the same in all these proofs, but in each case we have to do something specific to that technique. So we're also able to recover channel simulation results, resolvability results, etc. So here's the concluding slide. Basically, we give you a technique for obtaining this is a technique for obtaining a point in a Poisson process with specific distribution is already due to Abbas El-Gamal and Chukting in his life as a graduate student. What we did was to think about what happens when you're trying to figure out how close one distribution is to another. And as I said, we've got a much bigger paper that I haven't talked about at all, which studies the situation when you have lots of distributions. In fact, we can, for instance, one beautiful result is that if you take all possible probability distributions on a Polish space, you can create a simultaneous coupling of all of them, so that for any pair of them, the total variation distance is bounded by twice what you would get if you were just coupling the two of them. So the nature of those kinds of results are all in another paper which is not related to this talk. Also based essentially on this kind of technique, slightly generalized. And here are demonstrated applications in a whole bunch of traditional information theory problems. Now, one thing you could say is, we've actually been able to come up with these techniques for proving these results because we kind of knew what the answer was in the asymptotic case, right? So there's some proof of the pudding would be in coming up with something completely new. So there's always more that you can ask. So we've done something, but there's many, many ways you can go with this. And I think this is indeed the last slide. Thank you. Yeah. Yeah, so in this, as I said, we already know what to look for here. So, for instance, one interesting question might be, take something like the broadcast channel, right? Could you conceive of some scheme in the one-shot case which is completely different from Martin's way of thinking about it? Presumably that might show that Martin is not optimal or something, right? So we do have all these thoughts floating around, but... converse? Well, we are getting, I guess, the asymptotically optimal results. So we have not attempted, I don't think we have attempted to actually prove specific finite user lower bounds, if that's the question, yeah. But I suppose you could, yeah.